We're going to start off with Carol Hoffman from Essential Honeybees. He's been a master beekeeper for 25 years. He's from Central Michigan. Anyway, he's going to be talking about the beneficial bacteria suppress honeybee diseases. And with that, come on up.
Thank you. Okay, good morning. Everybody hear me all right? The talk we have today is microbials and honeybees. And I'm an EAS master beekeeper. I've had honeybees for over 25 years. The name of my company is Essential Honeybees LLC, and we're out of Ceresco, Michigan, which is in the southern part of Michigan between Chicago and Detroit. Okay, so microbials actually have 6 main classifications, but you and I probably have heard only 3 of them. And the main ones that most people know are bacteria, fungi, and viruses. And of course, as you can see in this cartoon, they also come in different colors. So bacteria are very small organisms. Of course, we can't see them with our eyes, and the spores are dormant, and if they're in the vegetative state, they're sleeping or growing. So bacteria are unique. They do not have a nucleus, but they do have DNA, and their biochemistry is very similar to other living things, which means that they eat. They don't eat a whole lot, but they eat and they replicate. And so they're very similar to other microorganisms. Now, can anybody here tell me what Langstroth called bacteria before the German scientist in Europe had actually coined the name bacteria? What did Langstroth call bacteria? He called it microfungi. Microfungi. So right now there's more bacteria on the planet than any other organism. They've been here a long time, probably longer than we have. They're found in the ground, soil, and in water, and they do live inside organisms, including the honeybee. Some of the bacteria, as we know, can cause diseases, but most of them actually help us in our everyday activities. This is a small graph of a typical bacterium. You can see the DNA is in the center, and you can see it also has a cell wall and a plasma membrane. And that's why it's so difficult to kill these things, because when they go to sleep, they have a really hard shell, and it's very difficult to actually cause damage to them or cause them to dry out. So bacteria enters the hive naturally from foraging bees, and they're collecting that from nectar and pollen and water. Other sources of bacteria can be from robber bees that are visiting other hives. The bacteria spores are very resilient, and some of the bacteria are very difficult to kill. Chalkroot is a disease that can kill the honeybee larvae. It is caused by a fungus. It's not a bacteria. It occurs worldwide, and it is very serious in some climates. Of course, the chalkroot kills the larvae and turns it into a white or gray mummy, and this is, of course, what chalkroot looks like in a frame. So they've uncapped these cells. The larvae did die. They were consumed by the fungus, and there they are. And that's what a bottom board looks like. Just think how many nurse bees we lost because of that chalkroot. And of course, the nurse bees eventually, because of the juvenile hormone kicking in, they turn into truck drivers, and we got foragers. So we lost all of those foragers, which are literally hundreds and thousands of bees, or I suggest to you even pounds and pounds of bees. So usually the larvae die from chalkroot within 3 to 4 days of infection. And then usually after 2 days of the cell being capped, the bees recognize that the larvae is dead, and they uncap it and start cleaning out the cell. The chalkroot spores can be transmitted in contaminated pollen and also drifting of bees. So if one hive has it in an apiary, the high occurrence rate is that other hives are going to pick up the chalkroot too. Also, sometimes you could have robbing bees going on from contaminated equipment, and they could bring the spores back to the other hives. Let's talk about European foul brood. I'm amazed how many people don't know what causes this. It is characterized by dying larvae. Usually you can tell it by the color. They're not pearly white. Some of the colors that might be evident would be red, brown, and yellow. Other names for European foul brood, especially down on the floor, they call that the crud. Latest research on European foul brood says that this is actually a collage of up to 5 or 6 different bacteria that can cause European foul brood. It's ingested by the honeybee larvae, and then the bacteria actually competes for the food inside the larvae. You have to make sure that you don't confuse European foul brood with American foul brood because it's completely different causal agent, and of course it produces different symptoms, and of course your control requirements are drastically different. Sometimes European foul brood is caused from a nectar dearth where the honey flow was slowing down. And then also, if you do hard splits and there's a shortage of young nurse bees, you'll see a higher incident of European foul brood expressing itself because there's not enough nurse bees to actually inoculate the larvae with the beneficial bacteria. This is a graphic picture of some European foul brood. You can see there that this one larvae is very yellow indeed, and eventually all of those larvae that have EFB will die. So those are not viable, and again, I suggest to you that losing larvae, losing nurse bees, and losing foragers is not a good thing. So American foul brood, AFB, is caused by Cannabacillus larvae, so it's just recently been renamed again. And it is the most widespread bacteria disease and the most serious for the foul brood. It has a very characteristic odor, so I just want to show of hands. Who here has smelled foul brood and knows what it's like? Okay, so I will share with you, only half of you listed your hands, okay? And that's not a good thing, because if you open up a hive and you don't happen to see the brown gravy and you don't know what the smell is, then you're in trouble. So I suggest that if you don't know what foul brood smells like, and if the opportunity expresses itself to have someone share with you what that is, please express yourself to have a good learning experience so you can understand what this disease is. Okay, the American foul brood spores are extremely resistant to drying out. And we've got a lot of data showing that American foul brood spores can survive in honey and beekeeping equipment for decades, 40, 50, 60 years. The numbers just keep going higher and higher as people have data showing that American foul brood is very resilient. A lot of people prophylactically treat for chemical treatments to try to abate and suppress the American foul brood. Remember, it actually can develop resistance to this antibiotic resistance. So what's the antibiotic that now doesn't work very well for American foul brood? Terramycin, correct. So terramycin now is not working very well. So if you have an outbreak of American foul brood, and if you apply terramycin, the odds are it's not gonna work. Okay, and of course, what are we using in place of that? Tolosin, exactly right. And then what's the risk of putting the tolosin into the hive? You could put too much in or feed it liquid and not follow the directions, and you could end up where workman honey would reject your honey because there's antibiotics over 200 parts per billion in the honey. So you have to be very careful with tolosin. This is an example of what's called the Ropey test. This is a positive confirmation of the Ropey test. I call this brown gravy. So the other thing I want to suggest to you is that please don't use your hive tool to poke at these cells. Get yourself a stick or a wooden skewer. I actually like little bamboo skewers that they do shish kebabs on. So I always have a bag of those and some nitrile gloves at hand. So if I'm going to be inspecting a frame that I think might have American foul brood, I always am very cautious and I don't use my hive tool when I poke at the cell to investigate it. Okay, so hives that are contaminated with the spores of American foul brood have to be basically prophylactically treated forever. Once the treatment is suspended, usually the outbreak occurs again, so basically the American foul brood comes back. And again, as we had suggested here earlier, that the terramycin that people are using doesn't seem to be working. It looks like we found it. So now there's 5 characteristic indications that this frame has American foul brood, and let me list all 5 of them for you. First off, a spotty brood pattern. That does not look good up there. 2 is the dark greasiness of the cappings. 3, if you looked at the cappings closely, you see some of them are sunken. They're not bulging up, they're actually concave or going down. The other one is some of the cells actually have cappings that have perforations in them. And then I apologize, the picture doesn't indicate it, but there's actually a lot of cells on here that have what's called black scale. And black scale is the American foul brood infected larvae that dried down And how many spores are in one black scale? Can anybody tell me what the number is, the magnitude, just a wild guess? Millions, exactly right. Millions and millions and millions of spores in one black scale. So it behooves you to remove these from your hive immediately. Okay, so we decided to run an experiment and a trial this summer, actually late summer, early fall, and we decided to set up a microbial battle where we would have bacteria attack bacteria, and we wanted to see what would happen. We actually run trials and we run control groups, and we actually used other than just one product. We removed the infected combs, the ones that I just showed you earlier, and we applied lactobacillus bacteria to the hives every week. And I worked at this yard for 6 weeks and a couple of the yards that had the outbreak of the American foul brood. And we took pictures, we froze bees, we sent samples into Beltsville Bee Laboratory, but we did not apply terramycin. And the reason why we didn't is because the apiary, the owner of the bees, had already applied terramycin in the springtime, and we already had an outbreak of American foul brood in the fall. He was unable to secure Tollicin because, as you know, the word got out that it wasn't going to go for over-the-counter sales, and it all went crazy, and I don't know if you can even buy any right now. It's probably like double the price. So we did not apply antibiotics, and lo and behold, after 6 weeks, we found that the bacteria actually abated the American foul brood. And so instead of burning almost 50 hives full of American foul brood, we were able to take them, migratory beekeepers, able to take them down to Florida. So right now, he gave me last week another phone call. The hives are thriving. They have nice capped yellow brood in them, and the hives are actually doing very well. This came out of the University of Sweden, actually Lund University, and we contacted Eva here and we got permission to use her picture. This one's just a couple years old. This was on one of those white paper research things, and basically she grew Patabacillus in a petri dish, and then in the center she actually applied Lactobacillus larvae, Lactobacillus, the bacteria, LAB. So you can see that it actually did push back the American foul brood, but remember, it only suppressed it. It didn't kill it, it just kind of abated it. So let's talk about some of the good bacteria just for a moment. These are some of the names that eventually more of you will have familiarity with, because it's going to be in more of the literature, it's more of the talks, it's the cutting edge. So Lactobacillus, Bifido, and of course Alpha 2.2. But what's unique and what we're now discovering is that these microbials excrete what are called peptides. And peptides are antimicrobial substances that one bacteria uses to compete with another. And so there's the 4 names of the antimicrobial peptides in these microbials. And you can see on the reference of this research that was done in 2004 there that they found a 28-fold increase in these peptides when these microbials were actually added to the environment that the honeybees were in. So the research showed that Lactobacillus, the Bifidobacterium, significantly increased the amount of peptides found inside the honeybee environment. Okay, this is not my circle of bacteria, but that's what I call it. These are RNA DNA sequencing. Those are called S16 numbers. And you can see on the left-hand side, there's one lactobacillus called Kinkii. There's a lot of research going on with this right now. And again, some of the research looks like it has some efficacy. Some of it's looking like it doesn't have efficacy. But to be honest with you, though, I think that what they're doing is they're trying to pick on just one little microbial. And I will suggest to you that to have a healthy ecosphere of microbials, you actually have to have all of them there in the sandbox to play nice. So these are not the pathogens, these are actually the good microbials. So microbials do work for the benefit of honeybees. Yeast, bacteria, and molds actually produce enzymes, vitamins, B vitamins, and antimicrobial substances and other essential things that the honeybees need to actually abate some of the diseases that they work with. The lactic acid bacteria, of course, in the crop or the stomach of the honeybee helps in the first steps in preparing both pollen and nectar for storage. So the honeybees face a lot of different diseases, that we shared some of them earlier here, but they actually use a diverse set of the group level defenses to prevent disease. So it's not like white blood cells. They don't have an immunity. That's not where their immunity is. So one of the ways that they can do this is through the shielding effects of the microbial community. And so that's what that circle of bacteria was talking about, is some of that community. So the relationship honeybees have is now indicating and pointing us to a potential control strategy for bee diseases. And there are several research scientists that are working on different microbial inoculations. And I suggest to you that within the next 5 or 10 years, there's going to be a lot of different microbial inoculation products that are going to come out into the market. I've spoken to people from Bayer Life Science. They're working on it. I've spoken to people from Monsanto. They're working on it. And we even have Purina working on it. They hired 2 scientists last year just to work on microbials for honeybees. And so this is the good news. The effects actually are against many different diseases, specifically the gram-positive bacteria, Patabacillus larvae. So some of the treatments that we use are for diseases like Nosema apis and Serena. So it's a microsporidium that's recently been reclassified as a fungus. It is the spores of Nosema are sensitive to some chemicals such as anhydrous vinegar, which is glacieracidic acid. Fumagillin, the drug, is a very complex molecule that is an antimicrobial agent. So it is a drug. As a matter of fact, if you ate fumagillin, you would get sick. It actually could harm you significantly. It was originally used on Nosema apis for the infections in the honeybees. This is some Nosema spores that are under the microscope at 400x magnification. Who here actually has a microscope and actually does sampling for Nosema? Okay, I got like 6 or 7, that's very good. So actually you need a few more people out here. Randy Oliver was suggesting some microscopes that can be used. The cost has gone down significantly, and so I think for like $300 or $400 you can get a very nice microscope that can actually do this work. Just pull the honeybee apart, you find the midgut, add some water to it, put it on the slide, and you start looking for these guys. This is the picture of the bottle of the fumagillin. This is a pharmaceutical drug. It is very expensive, and if you buy cases of this stuff, you're not spending hundreds of dollars, you're spending thousands of dollars. And the sad thing about this product is that sometimes it works and sometimes it doesn't. So we found in our data that fumagillin significantly reduces the beneficial bacteria found in the honeybee. The data we got back from the laboratory showed a 10-fold drop in the good bacteria. We also found that secondary infections can occur when you treat with fumagillin. So basically you're knocking out the good guys, and now you can get some chalk brood going on, now you can get some European foul brood going on, or some other infection, or maybe you get like a rebound of the Nosema, because a lot of times when you treat with this product, it drops the Nosema counts down, and then they just bounce right back up again. So one of the things when you destroy the digestive bacteria in the honeybee, you find that it has a negative impact on them, because now they can't eat, they can't digest the food. And so a lot of times when you feed fumagillin to the honeybees, they stop consuming food for at least a week or 2. So my takeaway here is that antibiotics significantly reduce the beneficial bacteria found in the honeybee. That resistance the bacteria has to antibiotics is a common phenomenon. It's happening all over the world. And that antibiotics only mask the symptoms, and they are not a cure. These are some of the treatments that we've got data that can impact microbials. The essential oils that we put into the hive have antimicrobial properties by nature. We found that any of the acids that we put in the hive, or the varroa mites, could potentially harm bacteria, both the formic and the oxalic acids. We have a lot of data on the fumagillin where the antimicrobial, antifungal agent is negatively impacting the beneficial bacteria. And then of course, terramycin, tolucin, and lincomycin are registered for use in honeybees, and as an antibiotic drug, they do harm the beneficial bacteria. This is the slide that's been shown, I think, 2 or 3 times here at the conference, so I apologize for the repetition here. But I think this has a lot of takeaway. We've got 9 years of data here, and you can see by the brown-orange that we now have what's called the total annual loss. And for the last year, for everyone who participated in the survey, you can see that we had over a 40% loss for our honeybee population. As far as I'm concerned, that's unacceptable. I don't know how we're gonna stay in business if the bees die. You've gotta have live bees to take the pollination contract and to raise queens and to make splits. We purchased the emergency response kits from the Bee Informed Partnership. We actually sampled live bees from our apiary in central Michigan and also put bees in bottles and sent them in. They were tested for 3 different things. We had our varroa counts performed, we had our nosema counts, and we also had our viral analysis from the live bees. On the left-hand side, you can see that our varroa counts were actually less than 1 per 100 bee, so that was actually good. And in a moment, I'm going to share with you how we did that. The nosema counts, you can see actually one is colored red, and that's because it's above 1 million spores. So the healthy group was actually 0.21 million spores per bee, and that's average of the 8 samples on the one group and 8 samples in the other. But then the weak group actually had a very high incidence, and some of the individual samples from those hives actually had 3, 4, and 5 million spores of nosema per the bees that were sampled. And on the right-hand side, you can see, yep, we got the black queen cell virus going on. We have the Israeli acute paralysis virus, the Lake Sinai virus, and the deformed wing virus. Although I see it odd, though, that the weak group had the deformed wing virus, but the strong, healthy group did not have the deformed wing virus. So let's kind of like expand on that report there. So how did we get the mite count down? Well, it's not magic. You all know the answer. It's amitraz. In 2013, we treated, and I will tell you, I think we got like 99.9% knockdown. I couldn't find mites anywhere. And tell me I'm silly, but we didn't treat in 2014. We just said, we ain't doing it, stuff's expensive, and we're just gonna move on. But of course, we sell nukes and we raise queens, and my wife, who's a master beekeeper too, said we are not selling nukes full of varroa mites, and so we treated in the spring, May of 2015. So that's why the numbers are below 1 per 100. The other question here I'd like to answer for you, what are the 2 hive groups? We are doing controlled hive studies here. And so the healthy group was actually inoculated with microbials 3 times during the year, spring, summer, and fall. And then the weak group were not inoculated, that was the control group, and they were given just dry megabee. So the healthy group actually had only a 21% winter loss, and we took a beating on our control group, which actually had a 40% winter loss, and of course that was in central southern Michigan. So here's the bar chart, and it basically shows where we are in the state of Michigan. Again, this is Bee Informed Partnership data. And the state average for last year for Michigan was 30%. So 30% of the hives died during the winter. You can see our control group had a 40%, and the microbial inoculated group actually only had a 21%. So there's some correlation there, and these differences are statistically significant. We also sampled a lot of frozen bees. I have spent a lot of time with dry ice and ice packs and sampling nurse bees and sampling nurse bees and sampling nurse bees. And so what we did is we sampled, I think N is 50 down there, of the control group and the direct fed microbial treated group. The picture on the right-hand side is just one of the petri dishes that they were culturing to get those counts. And you can see the lactic acid bacteria group were significantly different. So basically you can see we got a bump in the good bacteria by actually putting the microbials in there 3 times a year. So here's my summary of my talk, and I'm really grateful for your time this morning. The microbials in the honeybee are very diverse. They're very complex in their interactions, and we're just now starting to understand these interactions with microbials. The beneficial bacteria have to be there because they suppress the pathogens like chalk brood and nosema and foul brood. So here's the takeaway. The inoculation with beneficial bacteria now has the potential to reduce the occurrence of disease. So we're now exploring that potential.